lecture 9. This is continuation of the previous two lectures on the topic of friction and its applications. In the last lecture, that is lecture 8, we started our discussion on belt friction. This is an important application of the concept of friction. With the help of belt and pulley system, we can transmit power from one point to another point. In the last lecture, we derived an important relationship for the tension in the two sides of the belt as it goes over the pulley or drum. Let's say the angle of wrap, that is the angle through which the belt is in contact with the drum, is beta. Then at the instant of impending slip between the belt and the pulley, the ratio of the tensions on the two sides of the pulley is given by exponential of mu s, that is the coefficient of friction, static friction, times the angle of wrap. If on the other hand the belt is slipping, that is there is relative motion between the pulley or drum and the belt, then this ratio of the two tensions on the two sides of the pulley is given by the exponential of coefficient of dynamic friction times the angle of wrap. Now, after having established that relationship, we also saw how to calculate the torque being transmitted by the belt when it has tension T1 and T2. Also, what is the force exerted or reaction exerted by the bearings on which the pulley is mounted, so that we should be able to calculate the necessary force to maintain the tension in the belts. Okay. Today we will take up few applications or examples of these concepts, and let's begin with example 1. This examples is shown here. A weight of a block of 120 kilogram is supported by a rope which is wound 1.5 times around a horizontal rod. So it is it can be easily seen that this is the block of mass 120 kilogram, and it is being held with the help of a rope which is wound on this horizontal rod. Knowing that the coefficient of static friction mu s between the rope and the rod is 0.15, determine the range of values of P. P is the applied force at the free end of the rope for which the equilibrium is maintained. So, well, when will the equilibrium be disturbed? When the mass either goes up or goes down. So, there are two cases to be examined. First, we will consider when the mass is going down. So, the force at this end, mass is given as 120 kilograms. So, mg, that is the force due to gravity, is mass times the acceleration due to gravity, that is 9.81 meters per second. So, you can see that this force, gravitational force W, is equal to 120 g newtons, which is 1177.2 newtons. Now, the angle of wrap between the rope and the rod, because it is going over 1.5 turns. So, in each turn the angle subtended is 2 pi. So, 1.5 times 2 pi is 3 radians. Now, when the impending slip is such that the mass is about to go up, okay, that is this end where P is being applied, the pull P is being applied is going down. So in that case the tension P will be larger than that of W. So P over W, that is T1 over T2, is replaced by P1 and P over W is equal to exponential of coefficient of static friction times the angle of wrap, which we have already calculated. So in other words, P is equal to 1177.2 as shown calculated here into exponential of 3 pi radians into 0.15. So it will be 0.45 pi. Okay, the angle is always to be given in radians. So this calculates out to be 4839.7 Newton. So when this much force is applied at this end, downward force, then the weight will go up. Okay. Now let's examine this case when the weight is going down. Okay. The other extreme case is that let's say this slip is such that the weight is just about to go down, then we will have W over P, okay, is equal to e to power the coefficient of static friction times the angle of wrap, or P over W is equal to minus of e to power minus mu s into angle of wrap. So doing the same calculation with only difference is that there is a minus sign here at in the exponent. So we will get the force equal to 286.3 newtons. Okay. So in these two extreme cases, when once the mass is going up, the other time mass is going down, the forces are 286.3 and 4839.7. So these are the two extreme cases. Any force in between the two, the weight will be neither moving up nor down, so the equilibrium of the weight will be maintained. Okay. So these are the limits of the forces. Let's take up another example in which we have a weight WB and another weight WA. The example reads like this: the coefficient of static friction mu s is the same between B and the horizontal surface. So this is the weight WB and this is the horizontal surface. So this coefficient of friction is same as that between the rope, this green rope, and the corner support C. So what it means that this mu s over here and mu s over here of the contact angle is same. If the two weights WA and WB are same, determine the smallest value of the coefficient of friction, static friction mu s, for which the system is in equilibrium. Okay. So we have to find out that coefficient of friction which will be able to just maintain, that is, it will be the case of impending slip. That's very essential to note down when the slip is likely to take place. Okay. That's the critical case, and anything beyond that, the slip will actually take place. So let's have a look at the free body diagrams. Now there are two free body diagrams here, one for the belt or the rope. So on one side there is a tension TA and on the other side the tension TB. Now on this side, naturally this tension will be due to the weight of the weight WA. So TA will be automatically equal to WA, and on this side let us say the tension is TB, so we can see a tension TB on this side, okay, and this we will calculate from the free body diagram of the block B. Now, the angle of wrap, first we will take up this support C, the forces at around the support C. So, the angle of wrap here is pi by 2. Okay. So, at the impending slip of B, first we will take up free body diagram B. So, let us see what are the forces on the block B. There is a downward weight W, because WA is equal to WB is equal to W. So, that we know, and a normal reaction upward from this horizontal surface onto the block. So, if we consider the summation of forces on the in the y direction equal to 0, then it is easily seen that NB is equal to W. Okay. And then we will look at, and also from third law of Coulomb for dry friction, we know that at impending slip the force of friction Fb on the block B is equal to mu times the normal reaction. So, mu s times W. Now, look at the equilibrium in the x direction. So, summation of forces in the x direction equal to 0. So, what are the forces? TB and FB. So, obviously, FB is equal to TB, and FB we have already found out, mu s times W. So, now we come to the support C, where the rope is going on through an angle of wrap of 90 degrees. So, TA over TB, that is, see, look here, when the slip takes place between the rope and the support C, at that time the block will also just begin to slip. So, the slip of rope and the support is same as the it is happening at the same instant as the slip between the block and the horizontal surface. So, it means we will use the coefficient of static friction for this exponent at that impending slip case. So, substituting for TA, which is equal to W, and then TB, etc., which is mu times s, mu s times W into exponential of mu s beta. So, simplifying, W and W will cancel out. So, we have this simple equation, coefficient of static friction mu s times exponential of mu s times beta is equal to 1, right, and it means that e to beta is pi by 2. So, exponential of pi by 2 times coefficient of static friction is equal to reciprocal of coefficient of static friction. This equation can be solved numerically. There is no closed form solution. So, solving it, we find that the coefficient of static friction A comes out to be 0.475, right. So, otherwise the slip will take place. If the coefficient of friction is less than that, the slip will take place. Yeah. We will take up another interesting example, a very practical example. This is about the differential handbrake. Suppose in a workshop or in your automobile there is a flywheel and we want to bring it to rest, then we use this handbrake or differential handbrake, which consists of a belt going over the flywheel or the drum, and the force is applied through a lever system as shown over here. So, the example reads a differential handbrake is used to control the speed of a drum. Determine the minimum value of the coefficient of static friction for which the brake is self-locking. That is, we do not have to apply any external force when the drum rotates counterclockwise. Okay? So, the drum is rotating counterclockwise. Well, this system is shown over here, various dimensions are given. So, let us go on with the free body diagram of the lever. Well, this is the lever, this is the pin joint about which the lever can rotate. So, at the pin there are the reactions Bx and By. Now, this is the applied force P, but since this system is self-locking, that is without application of external force, the braking action has to take place. So, we will set P is equal to 0. These are the ends of the belt which is going over the drum. So, TA on one side, TC on the other side. Okay. So, let us say take moments of all the forces about point B. Why we have chosen point B? Because two of the unknown reactions Bx and By pass through that point, and hence their moment about B will be 0. So, if we do so and P is already, the applied load P is already known to be 0, then we are left with TA and TC. So, taking moments about B and setting equal to 0 and taking the dimensions as given over here, 0.4 meters into TC, that is anti-clockwise, and this is TA into 0.15, that is clockwise. So, in this way 0.04 TC minus 0.15 TA is equal to 0, hence TC comes out to be 3.75 TA. So, the ratio of the two tensions TC over TA comes out to be 3.75. Now, we look at the free body of the free body diagram of the drum or the belt or the pulley. Well, for impending slip condition, since the applied torque is counterclockwise, so to break it, that is to bring it to halt, the torque due to the tensions of the belt should be clockwise. So, TC over TA is equal to e to power coefficient of static friction times the angle of wrap. Now, what is the angle of wrap? It is given as 210 degrees, which is equal to 7/6 pi radians. So, take logs on both sides. So, it means log of exponential will be mu s times 7 pi over 6. This is equal to TC over TA. Okay. And since we have already determined this ratio as 3.75, so log of 3.75, which comes out to be 0.3606, and from here we get the coefficient of static friction to break the motion of the drum, to bring it to stop, that comes out to be 0.361. So, that is a very practical example of friction. Let us continue with few more examples, so that we understand various aspects of friction. Here is the case of two pulleys pulley B is driven, so the B is the driven pulley by a diesel engine, and the pulley A is connected to a compressor which requires a torque of 500 Newton meters. What is the minimum value of mu s between the belt and the pulleys for the case when F, that is this tension at the bearings, is 2000 newtons. So, what is the minimum value of mu s? That is, if we have slightly less than that, slip will take place. So, it is the case of impending slip. Various dimensions, the diameters, etc. are given. So, let us begin with the solution of this problem. Well, first of all, we have to determine the angle of wrap on both the pulleys. For this, we make use of the geometry of the problem. The distance between the centers of the pulleys is given as 2 meters. The radii here is 0.7 meters, and of the smaller pulley it is 0.4 meter. So, let us say if I complete the parallelogram here, and this angle alpha can be easily obtained, sine of alpha is equal to, well, you can easily see that this angle here is 90 degrees. So, this makes a right angle triangle. So, 0.7 minus 0.4, that is this dimension, divided by 0.2 is over here, divided by 2, that is the distance. So, you look at this parallelogram. So, if this side is 2 meter, this side is also 2 meter. So, this is sine alpha. So, this is equal to 3, 7 minus 4, so 3 by 20, okay, and therefore, alpha is sine inverse of 0.15, which is 8.63 degrees. Now, for the pulley A, this is pulley A, this is pulley B. So, for pulley A, the total angle of wrap will be 180 degrees and 1 alpha here, 1 alpha over here. So, plus 2 alpha, okay, with that is beta A is equal to 180 plus 2 times 8.63, which comes out to be 197.3 degrees. On the other hand, when I go to pulley B, then the angle of wrap beta B is equal to 180 minus 1 alpha over here and 1 alpha over here. So, that will come out to be 162.7 degrees, right. So, after having calculated both the angles of wraps, then we will analyze first the pulley A and then pulley B. Now, what is the information available to us? That is, the angle of wrap was found out to be 197.3, and also there is a total horizontal force from the bearing which is given as 2000 newtons, okay, and then the total torque is also known. So, there are 3 equations. First, the pulley equation, that is T1 over T2. First of all, we will consider the case, let us say at the pulley A there is slip just about to take place, that it is the case of impending slip at pulley A. So, T1A over T2A, that is T1A over T2A is equal to e to power mu s. Now, 197.3 is to be converted into radians. So, pi into pi over 180, because 180 degrees is equal to pi radians. So, 197.3 into mu s, which is unknown. So, we will have this ratio is equal to exponential of 3.44 mu s. And then we will consider the moments about the center of the pulley A, okay, T1A minus T2A. So into 0.7 is, this is given as 500 Newton meters, and solving this we will have the difference between the two tensions T1 and T2 for the impending slip at A is equal to 714 newtons. And then since the horizontal force component at the bearings is known, so we will take the components of the belt tensions in the horizontal direction. Each one, for example, on one side it will be T1A cosine of 8.63 degrees. On this other side also it will be T1B cosine of 8.63 degrees. Just to show you, let us say this is T1A, this is T2A. So we will take the horizontal components. So adding up the two, we will get T1A plus T1B is equal to 2023 newtons. So we have three equations, three unknowns, that is T1A, T1B and mu s. So the system can be solved, system of equations can be solved. The tensions T1A comes out to be 1368 newtons, T2B comes out to be 655 newtons, and mu s is 0.214. Well, you may be wondering, well, at the pulley A there is no slip, but at the same time there may be slip at pulley B. So we have to see whether there is slip at pulley B, or is this coefficient of friction, static friction 0.214, prevent the slip or not. For that we will do the similar analysis for pulley B as we have done for pulley A. So let us do that. Well, first of all, 500 newtons meters was the torque which was being supplied by the pulley A. So what will be the corresponding torque at the pulley B? Okay, that will be, you can easily say the MB over MA, that is the torque at B over torque at A is equal to the 0.4 divided by 0.7 in the same ratios as the radii or the diameter. All right. So you will have the corresponding torque is 286 Newton meters. Okay. Well, this equation comes from the work principle, that is the work done, if there is no friction loss, any other loss, then the work done by pulley A should be equal to work done by pulley B. So once again, the ratio of the two tensions T1B divided by T2B, that is when the slip is just impending at the pulley B. So suppose the corresponding coefficient of static friction is mu s dash, then e to power mu s dash times the angle of wrap at pulley B. Angle of wrap is known to us, that is it was calculated as 168 or something, 162.7. So which converts into radians as 2.84 times the coefficient of static friction mu s dash. Again take the moments about the center of the pulley B, with then the sum of the two tensions is 715, then balance of forces, that is reaction at the bearings, is again 2000 newtons, and this will again give me T1b plus T2b is equal to 2023. So again 3 equations, 3 unknowns, and if we solve it, we will get the corresponding tensions as 1369, 654, and most interesting of them all is mu s dash, which is the coefficient of static friction at the pulley B, which is required is 0.26. So for the no slip condition at pulley A, it was 0.214. So the new coefficient of static friction is greater than the previous one. So if we have this coefficient of friction, then there will be no slip condition at both pulley A as well as at pulley B. So this is the desired coefficient of friction, which will eliminate the possibility of slip everywhere. All right, just one more case. A flat belt is used to transmit a torque from drum B to drum A. So drum B to drum A. Here in this problem, that the coefficient of friction is already given, namely it is 0.4, and the allowable belt tension of 450. So the maximum tension at any point in the belt cannot be more than 450 newtons. Determine the largest torque that can be exerted on drum A. And here angle of wrap can be easily found out, because the inclination on the belt on both sides to the vertical is known, namely 15 degrees. So on one side it will be 180 plus 15 plus 15, that is 210, and on the other side it will be 180 minus 2 times 15, that is 150 degrees. So angle of wraps are known, the coefficient of static friction is known, the torque to be transmitted is known. So all we have to find out is the largest torque. Well, as I said, angle of wraps at belt A, it is 2 pi by 6 this will be 7 pi by 6, because pi and pi, yeah, this will be 7 pi by 6. 7 pi by 6 and 5 pi by 6. Okay. Since the angle beta B, that is the angle of wrap at pulley B, is less than the angle of wrap at A, that is less portion of the belt is in contact with the pulley B. So the chances of slip are higher at pulley B, mu s being same, okay, because the exponent in one case will be, in the case of B, beta pulley B will be less than that in case of pulley A, and hence if the slip is to take place, it will first take place at B. So that is our critical situation. So the maximum tension on the pulley B, T max, is calculated as T1. So T2 over T1 is equal to e to power mu s over into beta B. So maximum tension is known as 450. So T2 is found out to be 157.91 newtons. Okay. Yeah. Let's examine pulley B. The angle is 210 degrees. So you have T2, which is the T max in this case, is equal to T1 e to power mu s beta B, and this we have already found is 157.91 newtons. And then we look at pulley A. The torque transmitted clockwise is 100, how much was it given? Let us see. Well, the torque transmitted is to be found out. So, let us say this is MA is equal to the radius of this belt T into T2 minus T1, and this will be 450 minus 157. So, this will be 35.05 Newton meters. Okay. So, with the help of these 5 or 6 examples, we have examined various types of problems which can be tackled for belt pulley systems. Okay. Now, let us consider another aspect of friction, namely the rolling friction or rolling resistance. You might have seen that suppose a heavy roller is used on, let us say, on a cricket pitch. So, 2 or even sometimes more workers, they pull the roller on the pitch. Now, if we examine that case, suppose there is a heavy roller, weight is W, and it is rolling on a surface, a level surface. So, the contact between the wheel and or roller and the ground is a point contact through which a vertically upward reaction, normal reaction N is being applied. Okay. The pulling force is P. So, at the point of contact between the roller and the ground, there is a force of friction F, right. Now, let us examine the equilibrium or state of equilibrium or state of uniform motion in the same straight line, that is also equivalent to in a new inertial frame, that will be considered as a state of equilibrium. So, to examine that, I will take moments about the center of the roller. Now, W and N as well as P, they pass through the center of the roller. So, since the sum of all the moments is equal to 0, it means the force F is also having a moment equal to 0 about the center of the roller. It means that force F is 0, there is no force of friction, and hence there is no force of pulling force required to move the or to maintain the uniform speed of the roller, which is contrary to the experience. After all, the workers have to pull the roller to move it. So, where does this anomaly lie? The principles of mechanics or equations of equilibrium dictate that there should not be a pulling force P, but experience says that there is a pulling force P. So, to resolve this dilemma, let us look at what happens at the roller, at the contact point between the roller and the ground. Because of the heavy roller, the ground deforms. It will no longer remain as level ground, there will be a small deformation due to the weight of the roller. This can be examined by elasticity equations, but that is not absolutely essential for us to do. But let us say the ground has slightly raised up, and then again it will go back to the level value. So, this is under a microscope, you can say this is the contact position between the roller and the ground, and the normal reaction, instead of being through this point, will be now acting through here. Okay. So, now let us see if all the 3 forces P, W and N, they pass through the center, then the body will be in equilibrium, and then we can use the triangle law of forces to examine the equilibrium of concurrent forces. So this is exactly what we have done. There is a normal reaction N, the pulling force P and the weight W. So completing this triangle, we can say that W is equal to N cosine phi, okay. P is equal to W sine phi, and tangent phi is equal to P over W. Now in small angle approximation, sine phi is very close to tangent phi, and that is, both of them are very close to angle phi itself in expressed in radians. So we replace this tangent phi by sine phi, then P over W is equal to, if I go back to the picture here, this will be angle phi here, so you can see that if I complete the triangle, so this will be A over R, okay, that is sine phi. So P is equal to W A over R. This new constant A is called the coefficient of rolling resistance. Well, it's different from coefficient of static friction, mu, which was a dimensionless quantity. Here A will have in the dimensions of length, millimeter or meter, etc. Then A over R will become dimensionless and P will have the same dimensions as that of W. Now to fix our ideas about rolling resistance, let us consider an example. Here is a heavy plank weighing 10 kilonewtons, which is resting on two rollers or two heavy wheels A and B, and the distance from the ground is 300 millimeters, that is 0.3 meters, which is also the diameter of A and B, and each of the wheels is weighing 1 kilonewton, right. What force P is needed to maintain a steady motion to the right? Take the coefficient of rolling resistance between the rollers and the ground to be 0.6 millimeters. Once again note that the dimension of the coefficient is length dimension, and that between the plank and the rollers to be 0.4. So at these 2 points it is 0.4 millimeters. Well, the problem actually is very simple as well as very illustrative. First of all, let us look at the free body of the plank. This is the plank which is being pulled by a force of P. Now here we will invoke the argument of symmetry. The two rollers are placed symmetrically, or they are supporting the plank symmetrically. The total weight of the plank is acting through the center, 10 kilonewton. So due to symmetry of the loading as well as symmetry of the geometry, it is quite obvious that the reactions will also be equal. Same argument we had in the case of beams also, you may recall. So it means the reaction here and reaction here will be same, and essentially they will be both 5 kilonewtons because the total downward load is 10 kilonewtons. And since the coefficient of rolling resistance is also same between the wheels and the plank, so the friction force here will also be same, but the total force of friction is to be balanced by the pulling force P. So essentially it will be P by 2 and P by 2. So by symmetry arguments we have achieved some information, that is the friction force will be P by 2 and the normal reactions will be 5 kilonewton. Then we will look at the free body of each roller. Now once again I am looking at one roller. The normal reaction is 5 kilonewtons coming from the plank, and this will be acting at a point whose distance is A, that is coefficient of rolling resistance 0.4 millimeter. On the lower side, this point is in contact with the ground, and the coefficient of rolling resistance is 0.6 millimeter. So the distance will be 0.6 millimeter. The weight from the plank coming to the wheel is 5 kilonewtons. 1 kilonewton is the weight of the wheel itself. So the 6 kilonewton downward has to be supported from the ground. So the vertical component of the reaction will be 6 kilonewton. So we have found out all the forces acting on the wheel: 5 kilonewton, 6 kilonewton, 1 kilonewton, P by 2, and this will also be P by 2. The horizontal forces have to balance. Now you can take moments about this point or point O, either point Q or point O, both will amount to be same. And remember that these distances are very small. This dimension is 300 millimeters. So essentially what we will have is that we will P by 2 into, I am taking moments about Q, so P by 2 into 2R is equal to 5 into 0.4, okay, plus, so this is anti-clockwise and this will also be anti-clockwise, plus 6 into 0.6, 6 kilonewton. So this equation when simplified, PR is equal to 5.6, okay, because this 2 and 2 cancels out. So yeah, 2 plus 3.6, so 5.6. So P comes out to be 5.6 divided by 150, which is radius R, that is diameter is 300 millimeters, radius is 150, so 37.33 newtons. So with this simple arguments, we have seen that the pulling force required to move the plank as well as both the wheels to let them roll around on the ground is 37.33 newtons. So we have examined various types of friction problems, how the friction can manifest in various applications like thrust bearings, belt and pulleys, and then very important aspect is the rolling resistance, that is between wheels, drums, etc., and the rough ground, where the deformation of the ground plays an important role. So there are other possibilities of application, considering the applications of friction, namely in screws, like in screw jack or many other applications. Again, the force of friction plays a very important role in supporting the loads, etc. So we will close the chapter on friction and its application. We will start with the next topic in our next lecture. Thank you very much.